Hi guys, welcome to another grade 12 work, energy and power video. Today we'll be treating some question papers. Let's get to it. We're starting with question 5 of a certain question paper. The problem statement reads as follows. A 70 kilograms box is initially at rest at the bottom of a rough plane inclined at an angle of 30 degrees to the horizontal. The box is pulled up the plane by means of a light intangible held parallel to the plane, as shown in the diagram below. The force applied to the rope is 700 newtons. 5.1. What is the name given to the force in the rope? The force in the rope is called tension because rope provides tensional force. You know that. 5.2. Give a reason why the mechanical energy of the system will not be conserved as the box is pulled up the plane. Simple. It's because there are non-conservative forces available. The box is pulled up over a distance of 4 meters along the plane. The kinetic frictional force between the box and the plane is 178.22 newtons. 5.3. Draw a labeled free body diagram for the box as it moves up the plane. And the free body diagram is as shown here. I prefer to draw the free body diagram with components. As you can see, I'd like to break down the gravitational force into two components, Fg parallel and Fg perpendicular, as you can see on my diagram. But that's how you draw the free body diagram. 5.4. Calculate the work done on the box by the frictional force over the 4 meters. First step, I went on and written down my formula. Work done by frictional force is equal to frictional force multiplied by change in x multiplied by cos of theta. And substituting in everything I've just said, frictional force I was given is equal to 178.22. The displacement is 4 meters. And the angle is 180 degrees because friction opposes the motion. And hence the frictional force will equal negative 712.88 newtons. 5.5. Use the energy principle to calculate the speed of the box after it has moved 4 meters. And I've cleared the previous questions to make some space. I've only left the free body diagram because that's going to help me in this question. But the first step will be, I write down that formula, work energy formula, which states that work net is equals to change in kinetic energy. And expanding that formula, I get the net work in this particular question is the work done by friction, the work done by force of gravity, and the work done by tension. That is the net work. 3 forces are applying. The work on this particular question is the tension, the friction, and Fg parallel. And as for Fg parallel, and I know that Fg parallel is given by mg sin theta, and the change in x is there, and the cos theta for work, plus tensional force, change in x again, and the again cos theta, that is the work done by tension. And they are all equals to 1 over 2 m Vf squared minus Vi squared. Substituting in all the values for the above forces, I get negative 712.18 plus 70 times 9.8 times sin 30 multiplied by 4 multiplied by cos of 180 degrees plus 700 multiplied by 4 multiplied by cos of 0. And they are all equals to half of 70 Vf squared minus 0. This is because the initial velocity of the box is 0 because we are told that the box starts at rest, and hence its initial velocity will be 0, and we'll be calculating for Vf. And now simplifying that a little bit, I get negative 712.88 minus 1372 plus 2800 is equals to 35 Vf squared. And simplifying further, I get 35 Vf squared is equals to 715.12. And solving for Vf, I get Vf is equals to square root of 715.12 divided by 38, which gives me a final velocity of 4.52 meters per second. Pretty simple. Now let's move on to 5.6. 5.6. When the box is 4 meters up the incline, the rope accidentally breaks, causing the box to slide down to the bottom of the inclined plane. What will be the total work done by friction when the box moves up and then down to the bottom of the plane? The net work done it will be double the work done when the box moves up the plane, and hence it will be 2 times negative 712.88, which is equals to negative 1425.76. This is because the path is exactly the same, the mass is still the same, and again the coefficient of friction is still the same because it's the same plane, and hence friction will double down. It's that simple. Now let's move on to a different question paper. This one, a problem statement reads as follows. A demolition ball is used by a crane to break the wall of a building. The demolition ball of mass of 1,250 kilograms is lifted by the crane to a point R at a height of 5.8 meters above its lowest position in 60 seconds. Ignore the effects of air friction. 5.1. Define the term power. Power is defined as the rate at which work is done, but you should be careful to state these theorems, definitions according to the exam guideline. Those are the only acceptable definitions. Here I'm just making you understand, or writing this down so that you understand what power is, but when it comes to defining in an exam room or in a test, use the exam guidelines definitions. Moving on to 5.2. Calculate the average power dissipated by the crane in lifting the demolition ball to point R. Here, first thing is that power is equals to work done divided by time. You know that formula. And now, I substituted in the work done as change in potential energy, and I've neglected the kinetic friction. Why? Because at start, the crane and the ball was at rest, having zero velocity. And finally, again, it came to a rest, and hence the final velocity was 0 because the crane came to a stop, and hence 0 minus 0 will give me 0, cancelling out the change in kinetic energy. This doesn't mean that kinetic energy was 0, but the change in kinetic energy was 0 because the change in velocity was 0. Now, substituting in all the values, I get power is equals to 1,250 multiplied by 9.8 multiplied by 5.8, all divided by 60, and that gives me a power equal 1,184.12 watts. Moving on to 5.3. 5.3, define the term conservative force. Conservative force is a force at which the work done is path dependent. And then 5.5. State the energy conversion that takes place during the downward swing of the demolition ball. The ball started up at a higher height, and hence it had maximum potential energy, and moved on to a lower height with lower potential energy. The only energy that was present when the ball was at rest at R is potential energy. But then again, it started moving, and we all know that moving objects possesses kinetic energy, and hence, as it starts moving, that potential energy starts being converted into kinetic energy. And hence, the energy conversion that takes place here is what? Potential energy to kinetic energy. You get 1 mark for that. And moving on to the last question, which is 5.6, it says, using energy principle, calculate the magnitude of the average force exerted on the ball while it moves into the wall. So I've written down the formula. Change in potential energy is equals to mg hf minus hi, and substituting in the values, I get 1,250 multiplied by 9.8 multiplied by 0 minus 5.8, and that will give me a change in potential energy of equals to negative 51,050 joules. Now I'm gonna go and look for change in kinetic energy. I've told you previously that as the ball starts moving, that potential energy starts being converted into kinetic energy, and hence at the point where the ball comes in contact with the wall, all the potential energy has been converted into kinetic energy, and hence the kinetic energy as the ball hits the wall will be, the kinetic energy will be the potential energy, but it will be negative because it has been converted, and hence the kinetic energy will be 71,050 joules. Now moving on to the next step. Now I go on to write the formula work net is equals to change in kinetic energy, and expanding that formula I get force that was exerted on the wall multiplied by the displacement multiplied by the cos of 0 is equals to kf minus ki, and substituting in everything I know I get force exerted on the wall is equals to 0.25. I was given that displacement multiplied by cos of 180 because that the force that the wall exerts on the ball it opposes the motion of the ball, and hence the angle is 180 and not 0, and they are all equals to 0 minus 71,050 joules. And simplifying that further, I get negative 0.25 multiplied by F wall is equals to 71,050 joules, and hence force exerted by the wall is equals to negative 71,050 divided by 0.25, and that is equals to 284,200 newtons. And we are done with that particular question. Moving on to the last question paper in this video. This one states, arrestor beds are used to help moving trucks to come to a stop when their brakes fail. The driver of a 30,000 kilograms truck driving down a steep road drives into an ascending arrestor bed inclined at 28 degrees to the horizontal, as shown in the diagram below. 5.1. State the work energy theorem in words. The net work energy states that net work done in the object is equal to the change in object's kinetic energy. The truck with failed brakes passes point A at the beginning of the arrestor bed at a speed of 33 meters per second. The average frictional force on the truck is 31,000 newtons. While the truck moves up the arrestor bed, ignore the rotational effects of the wheels. 5.2. Give a reason why the net work done on the truck while moving on the arrestor bed is negative. And the reason is the only two forces that are doing work are gravitational force and frictional force, and they both oppose the motion of the truck, and hence the net work done on the truck will be negative. 5.3. Use energy principle to calculate the minimum length of the arrestor bed needed to bring the truck to a stop. First, I went on to say work net is equals to change in kinetic energy, and expanding that formula I get work done by friction plus work done by gravity is equals to 1 over 2m Vf squared minus Vi squared. Substituting in the formulas, I get Fr multiplied by change in x multiplied by cos theta, that is the work done by friction, plus mg sin theta change in x cos theta, and that is the work done by gravity, and they are all equals to 1 over 2m Vf squared minus Vi squared. And now substituting in all the values, I get 31,000 multiplied by change in x multiplied by cos of 180 plus 30,000 multiplied by 9,8 multiplied by sine of 28 multiplied by change in x multiplied by cos of 180 is equals to half of 30,000 multiplied by 0 minus 33 squared. And simplifying that down, I get negative 31,000 change in x minus 138,024,64 change in x is equals to negative 16,335,000. And solving for change in x, I get negative 169,024,64 change in x is equals to negative 16,335,000. And hence, change in x will equal 96,64 meters. And I'm done with 5.3. Moving on to the last question, which is 5.4. It states, which arrestor bed, ascending or descending, will be able to stop the truck in a shorter distance? Explain the answer in terms of the forces acting on the truck. And that is simple. The ascending bed, because on the ascending bed, two forces are working on slowing the truck down. That is the gravitational force and frictional force. And if you look at the descending arrestor bed, only one force is working on slowing the truck down, and that force is the frictional force. The gravitational force is helping the truck speed up, and hence it will take longer to stop the truck on descending arrestor bed. And we are done with that question, and that brings this video to an end. Thank you for watching. To support the channel and help more students access free lessons, Please like the video and subscribe if you're new to the channel. For additional learning materials and updates, visit our website using the link in the description below. Keep studying hard and I'll see you in the next one. Cheers.